Today I'm going to be doing the CIE AS Physics 9702 October-November 2025 paper 31. So the first experiment is to do with oscillations. We've been provided with a double spring and two single springs, and we're told to slide the double spring and the two single springs onto the longer wooden rod as so, and to set up the apparatus as seen in the diagram, and to use bosses to fix the wooden rod approximately 5 centimeters above the bench, parallel to the bench. So these are our bosses, and this is our bench, and they have to be vertically higher by 55 centimeters. Okay, we're also told to hang a total mass of 270 grams from the double spring. The mass hanging is referred to as M. Record M. So they did say to use 270 grams, so hopefully your M is 270 grams. Don't forget your units for the full mark. Then we're told to gently pull the mass down through a short distance, and when released, this mass will oscillate. And we're told to take measurements to determine the period T1 of the oscillations, okay? So basically, we're just going to tug on this mass ever so slightly, not too hard, and it's going to oscillate. Now we should have a fiducial marker for the initial placement of this mass, so we know when an oscillation has been completed. So once the mass has gone up and down and past this fiducial marker, we have an oscillation. So initially what we do is we have it do a set of oscillations and then stop the timer on however many oscillations we have the mass has done, and then divide it by the number of times it's oscillated. So let's say 10 oscillations took 7 seconds, and then we did a repeat and 10 oscillations ended up taking 5 seconds. So then really 10 oscillations on average took us around 6 seconds. So one oscillation T1 would take us these 6 seconds divided by 10, which is equal to 0.6 seconds. Now to gain the 2 marks, first of all, what you would have to do is your T1 value has to be greater than 0 or equal to 0.5 seconds, and less than or equal to 1.5 seconds. Of course, the units matter. And then the second mark would be for doing at least 2 repeats, so 1, 2, as well as the fact that the number of oscillations have to be greater than 5, where 10 is our n basically, to gain the full 2 marks. Okay, so now if we're told to gently place the hook of the mass hanger near the center of the shorter rod, carefully adjust the position so it's approximately parallel, and again gently pull the mass down and then record T2 of oscillations. So for this one I did 10 oscillations, lasted us 5 seconds, so one oscillation is 5 divided those 10, which would give us 0.5 seconds. I didn't carry out any repeats or anything like that because it's only worth 1 mark, so it's not worth the bother. The only thing needed to gain the mark is T2 needs to be less than T1. This makes sense because now we have 2 short springs that are in parallel, which will make the system more stiffer and more stable. So the mass is going to oscillate far less than it were to when it's hanging from one long flexible double spring. We are then told to vary M 5 times and to determine T1 and T2 for each, as well as the square root of T1 and T2 for each as well. So this is worth 8 marks. Now your first 4 marks are from overall having 5 sets of readings, also having correct trends with T1 and T2. As the mass increases, so do T1 and T2, and then as well as not having received help from the supervisor to score all 4 marks. Okay, then for the other 4 marks, first one being your mass has to be in between 220 to 350 grams. Your column headings must contain a quantity and a unit where appropriate. So in the same way that I did this, all my units are present. Then our third remaining mark after the 4 is that all values either to the nearest 0.1 seconds or 0.01 seconds. It has to be consistent, most likely with your stopwatch. I just chose to do it to the nearest 0.1 seconds just to make life a lot easier for me. And then the last mark remaining is for correct calculations of the square roots of T1 Okay. It then tells us to plot a graph with the square root of t2 on the y-axis and the square root of t1 on the x-axis. And then to draw the line of best fit and to determine the gradient and the y-intercept of this line. Okay? So what I've done is I've just gone up and I've plotted all my plots. Here's the table that I drew out, and I'm just going to draw a line of best fit. I'm just gonna take my ruler and try and get it as best as possible. Oh, sorry, wrong thing. And then I've identified this one as an anomaly because it just doesn't seem to fit in as well, okay? So, our axes must be labeled in the correct quantities. Scales should be so that the plotted points occupy at least a half of the grid. So this is half of the grid. So it has to occupy more than half of the grid. Scale markings are no more than 2 centimeters. So this would be 1 centimeter. This can be no more than 2 centimeters. Sensible scales, nothing awkward. So I've just went up in 0.1 seconds to the power 0.5. And all this is for 1 mark. For the second mark, all points need to be plotted. So all observations that we have made have to be plotted on this graph. They should be as accurate as possible within half a small square or less. Points, in both directions. That's for your second mark. For your third marks, the trend of points must be positive, so going up in this direction. And then all points in the table must be plotted for this mark to be awarded. And it really just must be a straight line with the axes the right way around. And yeah. Now our fourth mark is those are our 3 marks. Our fourth mark, it's a mark on its own, the line of best fit. So I've drawn our line of best fit, but let's take a look at what makes our line of best fit deemed suitable. So, has to be done by at least 4 points, based on 4 points. It doesn't have to go through all 4. There has to be even distribution of points on either side of the line. So I have 1 here and 1 here. So it's even on both sides, okay? Then, also the line must not be kinked. It has to be thin. It has to be straight. So ideally use a ruler. And it can't be thicker than half a square, like we said. If we do find an anomalous point, like here, you have to identify as anomalous by circling or labeling. I've just went with circling. There has to be, again, at least 4 points remaining after the anomalous point is disregarded to gain that 1 mark, okay? And then we're told to find the gradient and the y-intercept. So, now, so the one we could go for, the y-intercept, is the most easiest one. That is when x equals 0. So we could just go to our graph and see when x equals 0 right here. As you can see, we have chosen a scale so that there is a difference of 0.1. And those are 20 little squares. So really, and it's right in the center. So the same way, this would be 0.65. This would be 0.625. Now for the gradient, we're going to try and take, we're going to do rise over run. We're going to try and take as big as a portion of the line as possible so that we can get a more accurate value. So I'm just going to go with this one right here. Because it lies on 0.7 nicely. And then, okay, across would be our run. This would be our rise. So our rise is 0.7 and our run is 0.8 minus 0.625. Okay, 0.7 over 0.8 minus 0.625. That is our gradient. Okay, that is the equivalent of 0.7 over 0.225. And then when we take these two, divide them by each other, that leaves us with 3.11 as our gradient. Now to get the full 2 marks, you needed to first of all read off of x equals 0, or you could use another method like using y equals mx plus c, for example, but I just went with the reading of the graph, and it has to be accurate to half a small square in the y direction. Then for the gradient, it has to be consistent with the line drawn. The hypotenuse of the triangle should be at least greater than half. So half would be, actually it'd be a little less than that. Would be around here, I'd say. So a little greater than that. And both read-offs need to be accurate to half a small square in both directions. Also, the method of calculation must be correct if you choose, yeah. Okay, now for E, it says, it's suggested that the quantities are related by the following equation, the square roots of T2 and T1, where P and Q are constants. Use your answers to determine the values of P and Q. Don't know why I have that this here. So clearly it's in the format y equals mx plus c. So P is clearly our gradient, our 3.11, and Q is clearly our y-intercepts is 0.625. It says to give the appropriate units. Now, a gradient is a change so it's the rise over the run. Both the y-axis and the x-axis are in the unit square root of s, so these two would cancel out. So the gradient doesn't have a unit value, but the y-intercept is when x equals 0. So we're just taking the units for the y-intercept, so it would have a unit of root s. Okay. Now we're investigating the deformation of paper cylinders, and we're given 2 pieces. This is the smaller piece of the paper, and we have to record W, which is our width. So just take a ruler, and I'm just going to say it's 5 centimeters, for example. Okay, so then we're told to roll this paper into a cylinder and hold it in place using 2 paper clips, like shown in the diagram, and then to calculate the diameter we have created. We try to get it as close to 7 centimeters as possible and record to D. So you might not get 7 centimeters exactly, but I'm just going to pretend that I did. And that's completely fine, by the way. To get these 2 marks, what you need to do is your D has to be at least greater than 6.5 and less than 7.5 centimeters. There's also needs to be evidence of repeats. So I haven't displayed that here, but basically you'd measure once, twice, 3 times, and then you just note down the number of times you measured and the measures you got. Okay? Then it says to slide the loop of the upper spring onto the wooden rod like so. Then hang a mass of 200 grams from the lower spring like so. And then adjust the height of the boss so that it is approximately 10 centimeters above the bench. That is the mass. Then place this paper cylinder so that the middle of the cylinder is under the mass, so right underneath. And then the length of the springs is y. Measure and record y. I've went with 20 centimeters. Yeah. Actually, I don't know why. 20.0 centimeters, because our ruler probably is to the nearest millimeter. So our y range should be between 15 to 30. Yeah, and it's to the nearest millimeter, so you have to have that 0.0 so that it's in line with the accuracy of your ruler. Then it says estimate the percentage uncertainty in your value of y and to show your working. So the ruler that we have measures to the nearest 1 millimeter, which is equivalent to 0.1 centimeters. Because our measurement is in centimeters, our 20 centimeters, what's it called? I'm going to be using centimeters. I've converted the millimeters into the centimeters. The percentage uncertainty is the absolute uncertainty over the measurement made times 100. Now, it is an estimate, and realistically speaking, a 1 millimeters is the minimum uncertainty. So really, it could range from anything from 2 to 6. So I'm just going to go with 2. Okay. So 2 is our uncertainty over 20, which is our measurement, times 100. Which would give us an uncertainty of 10%, okay? Now, to gain these marks, you needed your absolute uncertainty to be within the range we've just stated, because realistically speaking, that's where it would lie, and this is just an estimate. We have to use the correct method, and this is that we use this formula. And if repeated readings have been taken, then the uncertainty can be half the range. For example, it doesn't have to be this high because you've taken multiple readings. But it can't be 0 even if your values are equal. Okay? Then it says to adjust the height of the boss just so that the lower mass squishes the middle of the paper cylinder until the mass is now 2.5 centimeters above the bench as shown. The length of the springs is now P. It is then asking us to record P. So I've gone with 19 centimeters instead of 20 centimeters. That is because now the weight of the mass is not just being supported by the springs alone, but also by the paper cylinder. So as a matter of fact, the value of P is going to be less than our Y, and that's essential to gaining this mark. Then it says to calculate Y minus P. Our Y was 20, our P is 19, so subtract them from each other, you get 1, so 1.0 centimeters. Correct calculation gives you that mark. It then says to use the larger sheet and to repeat all these steps all over again. So I've gone for a greater width. I've just gone from 5 to 6 centimeters. For the diameter, I went from, I believe, 7 centimeters to 8 centimeters. Our Y, I kept the same, so 20 centimeters. But the P has to be lower, 18 centimeters, because we have larger paper, so even more support from the paper. So our new Y minus P is going to be 2.0 centimeters. It's a subtraction of these two. Okay? And obviously, to gain these marks, you just need these two offer one mark, these two offer another mark. And another mark is for our second P being P2 being less than P1. Okay? Then for our next bit, we are told that this is the relationship between W, Y, and P, where K is a constant, and to just calculate two values of Q. Okay? So for our first one, these are our values. So really, we're just gonna, let me just make K the subject. So W is 5, divide 1, which is just 5. And then for our second one, our W is 6, divide Y minus P, which is 2, which is 3. So really, we're gonna be 5 and 3. And then you just need to calculate K correctly for the first mark. It's only one mark, as well as giving our answers to one significant figure and no fractions whatsoever. Okay, then it says justify the number of significant figures that you have given. Yep, so I've just written down here that W and Y minus P, so the difference, are both to one significant figures, as you can see. So it only makes sense for our K to be as well. Okie dokie. Then it says, it is suggested that the percentage uncertainty in the values of k is 10%. Using this uncertainty, explain whether this supports what we have just found in our previous calculation. So what I'm going to do is I'm just going to find the percentage difference between the two and see if the uncertainty is actually 10%. Because if the percentage difference is around 10%, then that makes sense for it to be a 10% uncertainty. To calculate the percentage difference, I'm just going to take the absolute difference of the two values and divide it by the average of the two. Okay, so the absolute difference is 5 minus 3, which is 2. It's a positive value anyways. And then the average of the two, so 5 plus 3 divided 2 equals 4. And then 2 over 4 times 100, which is equal to 50%. 50% is much greater than 10. Therefore, the results do not support the relationship in E. Okay. Now moving on to the last bit, they've asked us to describe 4 sources of uncertainty or limitations for this procedure. You should state the quantity being measured and the reason. So it's not enough to say, oh, 2 readings aren't, it's not enough to say difficulty measuring so and so. You have to explain why. So the first error or issue would be 2 readings aren't enough to reach a conclusion. We only did it with T1 and T2. And not only with T1 and T2, we used 2 papers and then that's it. Second of all, difficulty measuring D, which is the diameter, because it's likely that the paper wasn't actually a circular shape. It could have been slightly more oval, for example. Then difficulty measuring Y/P, which is the height of the springs. This could be due to parallax error. It could also be due to a number of other things. So like your ruler isn't steady. Deciding the position of the end of the coiled section, for example. Parallax error is just like your eyes not being at level with the ruler. And it's just the easiest one to put down. Again, also there's difficulty squashing the cylinder in terms of it not being evenly pressed on, or only, for example, the middle being squashed and not the edges, for example. So it's not really even distribution. Then it says to describe 4 improvements that could lead could make this experiment better. So we could say take more readings, that's the solution to our first issue, and then plot a graph. Or for example, compare K values, you could say. And then 2 to 4 would just be improved methods of how you would measure. So they did say, for example, for measuring D, we could, for example, use tape for a cylinder so that D is more accurate. For example, there's also, for example, we did say there's an issue with the ruler. You could say that it's not steady. You could clamp the ruler so that it is. There are also other improved methods. There's honestly quite a bit. They also said you could, for example, use a vernier caliper. Also, cover the whole cylinder by gluing a plastic oblong to the mass hanger so that you can ensure that the whole long cylinder is squashed as well. So really any methods that are sensible and solve the issues you mentioned in your first one.